Hello, thank you for watching, and welcome to the next video in my series on basic statistics. Now, a few things before we get started. Number one, if you're watching this video because you are struggling in a class right now, I want you to stay positive and keep your head up. If you're watching this, it means you've accomplished quite a bit up to this point. You're very smart and talented, and you may have just hit a temporary rough patch. Now, I know with the right amount of hard work, practice, and patience, you can get through it. I have faith in you. Many other people around you have faith in you, so should you. Number two, please feel free to follow me here on YouTube, or on Twitter, or LinkedIn. That way when I upload a new video, you know about it. And on the topic of the video, if you like it, please give it a thumbs up. Share it with classmates or colleagues, or put it on a playlist, because that does encourage me to keep making them. On the flip side, if you think there is something I can do better, please leave a constructive comment below the video, and I will try to take those ideas into account when I make new ones. And finally, just keep in mind that these videos are meant for individuals who are relatively new to stats. So I'll just be going over very basic concepts. And I'll be doing so in a slow, deliberate manner. Not only do I want you to understand what's going on, but also why. So all that being said, let's go ahead and get started. So this video is really the first in which we're going to explore the heart of what statistics is, and more specifically, sort of an undergraduate course in statistics. So inferential statistics is the foundation for almost everything we do in introductory and even more advanced stats. So what do we mean by inferential statistics? Well, if you look at the beginning of the word inferential, it's the root infer. Well, what are we doing when we infer something? That means we're making some conclusion or some evaluation based off of information that's not really complete. So we're sort of inferring that something is the case based on the data we have, sort of about something else or something else that's larger. And much of statistics is based around that concept. So in this video, we're going to talk about point estimation. Now, many times in statistics, we're interested in the property of a large population, maybe all the college students on a campus, or maybe all of the workers in a certain industry, or maybe when we're doing, say, in this example, in this video, we're going to look at statistical quality control. So a product is coming off the assembly line, and we want to check whether or not the quality is good enough. So we select samples off the ends of the assembly line, and we check them for whether or not they are within tolerance of our quality control. Now, we cannot do that for every product that comes off the line. So we select a sample of those, and then we sort of infer that if those are okay, then everything else coming off the line should be okay as well. And that's the idea about point estimation. We're making some estimation about a larger characteristic of a population using sampling techniques. Let's go ahead and take a look at an example. So our example comes from the field of statistical quality control. And in other forms, it's called Six Sigma and things like that. But this is a very basic example. So Highway Paving is a company specializing in residential road surfacing. Many of its clients seek out its specialized product, low-noise pavement. Recycled rubber can be added to the asphalt mixtures to reduce road noise, which appeals to environmentally conscious clients. So they make this special type of pavement, asphalt, that includes recycled rubber. And when car tires roll over this type of pavement, it reduces the road noise. Not only outside the car, which is good for the neighborhood, but also inside the car as well. Plus, it recycles rubber. And, old tires do not go into landfills. They get chopped up and put into pavement. So it's sort of a win-win. So the product is very popular. Now, one quality of the asphalt is called its viscosity, and that's its resistance to flow. So I'm sure you know about this concept in real life, like oil flows slower than water, and we call that sort of thickness its viscosity. Now, this asphalt must be maintained within very tight limits, otherwise it may be too thick or sort of too watery. So imagine trying to spread asphalt onto a road surface that is really, really thick and you can't really spread it out, or it's too thin and it sort of runs everywhere. So it has to be a certain viscosity. Now, for highway paving, the goal is a viscosity of 3,200. Now, I'm not going to go into the units of viscosity because they're not really relevant and they're kind of weird, so we'll just stick with the number 3,200. Now, during the manufacture of each batch of asphalt, the quality control specialist takes 15 samples of the material and tests the viscosity. This also ensures the batch has uniform viscosity. So, during each batch of asphalt, the quality control person will go into the vat or wherever it's kept and will take sort of 15 measurements or specimens within that batch and test or measure its viscosity. Now, a few things to note here. There's no way to test every single ounce of asphalt, which is the overall population. Therefore, the company must take samples. Now, from those samples, the company must then make inferences about the entire batch. So from these 15 measurements, these 15 specimens, they're going to make some sort of claim about the overall batch. So the inferences made using samples are by definition incomplete. So the 15 samples, what may or may not be an accurate representation of the entire batch. It's always going to be incomplete, but there are ways to ensure that our sampling techniques are good and valid. Therefore, the sample characteristics will always have some error built in. And that's one of the fundamental ideas in point estimation and in sampling. Whenever you're sampling from a larger population, it's never going to be perfect. There's always going to be some error in that estimation. So here are the 15 specimens that the manager took. So in the first specimen, the viscosity was 3193, and specimen 2, 3124, etc. So these are the 15 measurements. The first question is, what is the mean or the average of this overall sample? Now, I will pause here, and I'm going to slap myself on the wrist for doing this. When I talk about a sample, I am talking about the 15 measurements or the 15 specimens, not the individual measurements themselves. And sometimes I slip into those different terms. But when I mean a sample, I'm talking about the total of these 15 measurements. So what is the mean of the sample? Well, it turns out the sample mean here is 3210.73. So 3,210.73. Now, it turns out the standard deviation of this sample is 117.61. Now, we're not really concerned with the standard deviation at this point and where we're at in inferential statistics, but I just wanted to point that out to you. The thing we're interested here, probably more importantly, is the sample mean of 3210.73. Now, that's going to have its own distribution. So here's our sample. This is the curve that represents the sample of 15 specimens. Remember, our sample mean was 3210.73. Standard deviation was 117.61. So the mean of our first sample is down there at the bottom. And you can see that it is X bar sub 1. And that little subscript 1 means that's our first sample. Now remember, the company's goal is a viscosity of 3,200. Now our sample mean was 3210.73. Now since this is a sample mean, we do not expect it to be exactly 3,200. I mean, it could be by the sort of luck, but it's probably not going to be. But the question is 3210.73 close enough to our goal to be acceptable? So the quality control manager has this sample of 15 specimens, measures the viscosity of each specimen, and then comes up with a sample mean of 3,210.73. Is that close enough to the goal to put a check mark next to it and say, yep, this is a good batch? Does this sample accurately reflect the viscosity parameter of the overall batch population? Now, in previous videos, I pointed this out, is that when we use the term parameter, we're talking about the population. So the population mean is a population parameter. Our sample mean is the sample statistic. So parameters versus statistics. But is this sample good enough? Does it overall reflect the whole batch? Now, I know that the answer is yes. But the question is, how can we determine that statistically? And that's going to be something we explore in subsequent videos. So point estimation. What is this overall idea we're trying to get at in this video? What happens is we have some unknown population parameter. That could be the population mean, the population standard deviation, or the population proportion. And again, these are things we do not know. So we're going to use a sample to try to estimate them. Now remember, for the population mean, the symbol is mu. For the population standard deviation, it is sigma. And then for population proportion, p. Now what we're doing is we're going to take a point estimator. So for the population mean, our point estimator is the sample mean. For the population standard deviation, the point estimator is the sample standard deviation. And for the population proportion, the point estimator is the sample proportion. So those are X bar, S, and P bar. So we're taking our empirical data here on the right, and we're using that to make an estimation about some unknown population parameter. Now remember, point estimates are never perfect. They always have some error component in them. So this is commonly referred to as the margin of error, both in statistics and in sort of overall popular culture. So if you watch the polling during a presidential election, at least here in the US, I'm sure it's similar in other places, it'll say this percentage of people agree with this statement plus or minus 3%. Well, that's a margin of error, and this has the same idea. Now, technically, the error component is expressed as a confidence interval. So we are saying that we have some confidence that this point estimator is a proper representation of the overall population. And of course, we're going to talk about confidence intervals in upcoming videos. Okay, so that wraps up this very brief video. That is the beginning of inferential statistics, more specifically about point estimation. I just wanted to get across to you the idea that the foundation of so much of statistics, 95% of statistics, is about taking samples of larger populations and then using those as an estimation of the overall population. And of course, when we do that, they're never going to be perfect. There's always going to be some error involved, but you have to understand sort of how they come about. Okay, so that wraps up this video. Just a few things before we wrap up. If you're watching this video because you are struggling in a class right now, stay positive and keep your head up. You're a smart, talented person, and me and everyone else around you knows that. Number 2, please feel free to follow me here on YouTube, on Twitter, or on LinkedIn. That way when I upload a new video, you know about it. If you think there's something I can do better, please leave a constructive comment below the video, and I will try to take those ideas into account when I make new ones. And finally, just keep in mind the fact that you're on here trying to learn, try to improve yourself as a student, as a business person, or what have you, that's what really matters. I firmly believe that if you have the learning process in place, the results will take care of themselves. So, thank you very much for watching. I wish you the best of luck in your studies and in your work, and I look forward to seeing you again next time.